Hello, we are now on the last part of our lecture in Fundamentals of Engineering Mathematics. Here in Solid Geometry, we will be dealing here with figures in three-dimensional space. So unlike in plane geometry, where our concern is to solve problems of figures in two-dimensional, so here in Solid Geometry, the objects are in 3D. So let's start. First, let's discuss about solids for which the volume is equals to the area of base times the altitude. One example of which is the prism. Prism is a polyhedron in which two faces are equal polygons in parallel planes, and all other faces are parallelograms. So here are the examples of a prism. We have a rectangular prism, a hexagonal prism, triangular prism. So we have two faces parallel, and all other faces are also polygon. So we have here two face parallel for this hexagonal prism, and all other faces are also polygon. So what is the formula in computing the volume? So we have here two prisms. This one is an oblique prism, and the other one is a right prism. So as you can see, a right prism is where the base has perpendicular lateral sides or lateral faces. Unlike here, an oblique prism, we have an angle of inclination of the lateral faces of the base. So with respect to the base, so this corners here, or this lateral side, is not perpendicular to the base. So in order for us to compute the volume of an oblique prism, we need this perpendicular face, or the perpendicular area or perpendicular cross-sectional area with respect to the faces or to the lateral faces of the prism. Then multiply it to the length of the lateral side. For a right prism, just multiply the area of the base to the perpendicular distance or perpendicular height or altitude of that prism, which is h. For the lateral area or the area of the lateral faces of the prism, just multiply the perimeter of the base for the right prism, or the perimeter of this shaded region or the cross section of this one on the oblique prism to the lateral side. Okay, the length of the lateral side of that oblique prism. Same way here with the right prism, just multiply the perimeter or the perimeter of the base to the height. That's your lateral face or the surface area along the lateral faces. So if it is required here to determine the total surface area of the prism, just add the lateral face to the sum of the bases, which is twice the area of the base. Okay, for right truncated prism, um, if the lateral sides are not of equal length, which represents here as h1, h2, h3, in order for us to compute the volume of this truncated prism, We divide the area of the base by the number of sides of the base, which is this one, this one, that one, which means if this is a triangular prism, triangular truncated prism, we have a total of n, which is 3. Then multiply it to the sum of all the height from the vertex of the base. So in other words, take the average, okay, take the average of all the altitudes of this right truncated prism and multiply it to the area of the base. Okay. For the lateral area, just determine the area of these trapezoids formed by the lateral faces. Okay. So manually compute using the area of trapezoids. Next, let's answer this example. The side of the base of a regular hexagonal prism is 6 centimeters and its bases are 12 centimeters apart. Find its volume in cubic centimeters, lateral area in square centimeters, and the total surface area in square centimeters. So this is a regular hexagonal prism. So let's answer that. Okay, so here's the figure. If we have a hexagonal prism with a base of 8 centimeters, so if this is the base here, this is the cross-sectional base or the base, hexagon base. We have a side of 8 centimeters. Its bases are 12 centimeters apart, so we have an h of 12 centimeters. Determine A, the volume first. So since this is just a hexagonal prism, a regular hexagonal prism, we can simply apply the formula V equals to area of the base times the altitude. So let's find first the area of the base. So this is the base here. So let's just take one part of this regular hexagon by connecting the vertices to the center where we can form an isosceles triangle. Now, when we determine the central angle of that uh, triangle, which is 360 degrees, or just divide 360 degrees because that's the total angle of one revolution of, of angle from the center. Divide that by 6 since we have 6 parts here, 6 equal parts in terms of central angle. So we have an angle of 60 degrees. So if this is 60 degrees, it is expected that the other two angles are the same since this is an isosceles uh, triangle. Now, 180 divided by this angle here, theta. So let's assign theta, 2 theta, and subtract 60 degrees. It should be equals to 0 when we add these three angles. 2 theta and 60 should be 180 degrees. So to find theta, just subtract 180 by 60 and divide it by 2. So theta is equals to 60 degrees, which means this is an equilateral triangle. So this triangle is an equilateral triangle, is one, which means all of the sides are equal also. So if their interior angles are equal, their opposite sides are also equal. So that's 8 centimeters, 8 centimeters. To compute the area of the base, just compute the area of a single triangle and multiply that by 6. So for the area of the base, uh, going back here, the area of the base is 6 times 1 half AB sine theta. Okay, area of a triangle given two sides and included angle. So 8 times 8 sine 60 degrees. So the included angle is 60. Okay, area of the base is equals to 6 times 1 half times 8 times 8 times sine 60 degrees. So let's compute that. We have 166.277 square centimeter. Okay. Then multiply that area of the base to the altitude h. H is 12. 12. Okay. We have volume of 1995.322 cubic centimeters. Okay, next, find the lateral area. For letter B, the lateral area is equals to the perimeter of the base times h. So the perimeter, if we have one side equal to 8 centimeters, just multiply that by the 6 sides. So 8 times 6 divided by 6 and times the altitude 12. Okay, 12 centimeters. Okay, we have 576 square centimeters. That's your lateral area, or the area of the lateral faces or the sides of this hexagonal prism. Thirdly, what is the total surface area? Total surface area. For the total surface area, area total equals to the lateral area times twice the area of the base. So 576 plus 2 times 166.277. Okay, the area total is equals to 908.554 square centimeters. So that's the total surface area of this hexagonal prism. Okay, let's proceed to the next problem. Determine the volume of a right truncated prism with the following dimensions. Let the corner of the triangular base be defined by A, B, and C. The length AB is 10 feet, BC is 9 feet, and CA is 12 feet. The sides A, B, and C are perpendicular to the triangular base and have the height of 8.6 feet, 7.1 feet, and 5.5 feet respectively. So let's determine the volume. First, draw the figure, draw the solid, and here it is. We have 8.6 feet, 7.1 feet altitude, and 5.5 feet. So these are the length of perpendicular uh, or the sides perpendicular to the vertex of the base A, B, C. So given here, the length of sides of the bases 10 feet, 12 feet, and 9 feet. So this is a truncated prism. So the solution is the volume is equals to the area of the base divided by the number of sides times the sum of the sides A, B, and C, or the perpendicular sides with respect to the vertex of the base, or the altitudes of each sides. So we have H1, H2, and H3. So H1, H2, H3. Let's assign H1 here, H2, H3. First, determine the area of the base. This is the base here, which is a triangle with the given length of sides. So all sides are given. We can use Heron's formula. So using Heron's formula, the area of the base is just equals to the square root of S times S minus A, S minus B, S minus C, where S is the semi-perimeter, or the sum of all the sides divided by 2. Okay. So the semi-perimeter is 15.5 when we compute that. Now substitute that here. The area of the base is equals to 15.5 times 15.5 minus 9, 15.5 minus 10, 15.5 minus 12. The area of the base is equals to 44.039 square feet. Now, using again the formula here, the volume is equals to the area of the base, which is 44.039, divided by n, or the number of sides of the base, which is 3, and the sum of all the h. So h1 8.6, h2 7.1, h3 5.5. So the volume is 311.209 cubic feet. Okay. Now let's discuss another type of prism, which is the cube and rectangular parallelepiped. So they are also called as common prisms. Starting here on the cube, cube is also called as a regular hexahedron. Okay, a regular hexahedron, it is a polyhedron which 6 faces are all squares, or all of these faces are equal. All are equal. So that's a cube. All sides are equal, all faces are equal. Now, what are the formulas that we can use in computing the volume, area, diagonal, and space diagonal? For the volume, we have area of the base times the height. Okay, so if we assign A on one side with all other dimensions, just multiply the length, the width, and the height, which is equivalent to the A cube. For the area, surface area, total surface area of the cube, just compute the area of one face. So length times width, A times A. We have A squared, and multiply it to the number of sides, which is 6. For the face diagonal D, the face diagonal here is this one. So if we choose one face, okay, if we choose one face and we take the diagonal of of that face. This one is the face diagonal. So this formula is just derived from taking or using a right triangle form by this face. So if this is A, this is A. So this face diagonal is just the hypotenuse of this right triangle. So D squared is equals to A squared is A squared. So D is equals to the square root of 2A squared. So therefore D is A, the square root of 2. That's the face diagonal. And for the space diagonal, we have A the square root of 3. So this is the space diagonal from one corner to the other that is not of the same face. So we consider here three dimension, three-dimensional um, right triangle. So considering again this right triangle here, okay, we can solve this space diagonal. So before solving this S here, compute first this face diagonal, which is D, which is A the square root of 2. So if this is A the square root of 2, then take again Pythagorean theorem, S squared equals to A squared, because S is the hypotenuse. And the other one is A the square root of 2. So take the square of that also. Then compute S. So you have S square root of A squared plus um, 2A squared. So S equals to the square root of 3A squared or A the square root of 3. That's your space diagonal. For a rectangular parallelepiped, so rectangular parallelepiped is just all faces of a rectangular parallelepiped are rectangles and the two opposite faces are equal rectangles. So we have two equal faces, two equal opposite faces that are rectangle, and we have other four equal rectangles, which is this side, all of this lateral sides. So same formula applies in deriving the solution of the volume, the surface area, the face diagonals, and the space diagonal. We just use Pythagorean theorem by forming right triangles along this solid. So for the volume, we have this formula A times B times C, or the length times width times height. The total surface area, just compute the area of all the lateral faces and the other two opposite faces. And we have the diagonals. You can compute that using this formula or just use again the principles of Pythagorean theorem. And we have here the space diagonals. So same solution applies. So actually we need not to memorize these formulas as long as we know the uh, how to use the Pythagorean theorem in computing the diagonals. So let's answer some problems. A cube has a side of 6 centimeters. Determine the volume in cubic centimeters, total surface area, face diagonal, and space diagonal. So I think we need not to draw this. We can simply use the formula, or we can directly solve the problem by assigning A by 6 centimeters. So for the volume, volume is a cube. So 6 centimeters raised to 3 is 216 cubic centimeters. For the total surface area, 6a squared. The surface area is 6a squared. So 6 times 6 centimeters raised to 2. So when you compute that, that's 216 square centimeters also. Okay. For face diagonal, uh, the face diagonal D is a the square root of 2. So substitute again a by 6. So 6 the square root of 2, or that's 8.485 centimeters. And for S, we have a the square root of 3. 6 the square root of 3 is equivalent to 10.392 centimeters. These are the answers. Okay. Another example, the face diagonal of a cube is 4 the square root of 3. Find its volume. So given here, the face diagonal D. So recalling the formula for the face diagonal, which is a the square root of 2. Given the face diagonal, we'll be able to determine the uh, length of one side of the cube, or the length of side of the cube. So substitute D for the square root of 3. Then we have a the square root of 2. Divide both sides by the square root of 2. So that we'll be able to determine A. So we have an answer of 4 the square root of 3 over the square root of 2. We take the decimal form of that. Um, that is equivalent to 4.899 meters for the length of side. For the volume, have volume V equals to 4.899. We raise that to 3 because volume is A cubed. So 4.899 is 117.577 cubic meters. That's the answer. Okay. Another example for rectangular parallelepiped. A rectangular bin 4 feet long, 3 feet wide, and 2 feet high is solidly packed with bricks whose dimensions are 8 inches, 4 inches, 2 inches. The number of bricks in the bin is. So to compute the number of bricks in the bin, so if we have a bin here, first compute the total volume of the bin, then we divide that to the volume of a single brick. Okay, that way we will be able to determine the total number of bricks. Since we have a unit of feet on the rectangular bin and inches for the brick, we must be consistent on the unit that we will use before we apply it in this formula. So let's say we use feet on all the computations that we will use. So it means that we must convert these dimensions into feet. So converting inches to feet, just divide it by 12 in order for it to have a unit of feet. So this one would be 4 over 12 feet. 2 divided by 12 will be in feet. So we can now compute the number of bricks. First, the volume of the bin, given dimensions, length, width, and height. So L, length times width times height. That's the volume of that rectangular bin. So we have 4 feet times 3 feet times 2 feet. be divided by is 8 over 12 feet, 4 over 12 feet, 2 over 12. Okay, so we can directly solve that. Let's say the volume for the bead is 24 cubic feet. For the brick, when we compute that, we have 1 over 27 cubic feet. So divide that, we will have 648. So that's the number of bricks for this rectangular beam. Okay, another example, we have a packing box with dimensions 2 feet by 5 feet by 5.5 feet, completely covered with tin. How many square feet of the metal are needed, and what is the volume capacity of the packing box? Okay, so say this is the box. Okay. So we have sides A 2 feet, B 5 feet, and C 5.5. For the surface area A, because it will be completely covered with tin, so we need the total surface area uh, of this box. So for the surface area, we can use the formula that I presented earlier of 2 times AB plus BC plus C. Or you can just simply manually compute all of the lateral faces or all of the faces of this box, since all the dimensions are given, and add it. Okay, so we have here 2 times 2 times 5 plus 5 times 5.5 plus 2 times 5.5. Okay, computing that, we have a surface area, total surface area of 97 square feet. For the volume capacity, just multiply the length, width, and height. 2 feet, 5 feet, and 5.5 feet. We have total volume of 55.0 cubic feet. Okay, next, the cylinder. So it's also part of the solids, which volume is equals to the area of the base times the altitude. So still here in cylinders, uh, that formula is also still applicable, which is the area of the base is just to be multiplied by the height. Okay, so the only difference in cylinder is that the base, okay, cylinder is just a solid bounded by a closed cylindrical surface, and it has two parallel planes also. So here in cylinder, uh, most of the time we use a base of circle. Sometimes we ellipse is also used in a cylinder for the base, but um, the typical the typical solid, or the typical base that is always used when we say cylinder, is a circle. So again, applying the formula for the volume, area of the base times height, and for an oblique cylinder, this is the equivalent formula, and same applies with the lateral area, the perimeter of the base. So usually if it is circle, just the circumference of the base, times the length or the height. So again, let's solve some sample problems. An oblique circular cylinder has a lateral side with a length of 40 meters. If the base has a diameter of 4 meters and the lateral edge is inclined by 60 degrees with the horizontal, determine the volume of the cylinder. Okay, so this problem, we have a lateral edge inclined by 60 degrees, which means it is an oblique cylinder. So let's draw that. Okay, so here's the figure for this problem. We have a cylinder, circular cylinder, with a lateral side with a length of 40, right here, 40 meters. So, um, the base has a diameter of 4 meters, and this is the angle of inclination of the lateral edge or the lateral side, 60 degrees with respect to the horizontal. Now, determine the volume of the cylinder. In determining the volume of the cylinder, we can use uh, the formula area volume is equals to AR times L. We can use that. Or we can use area of the base times the altitude H. So here, what we only need if we are going to use this formula, which is the easier one, uh, we only need the value of the altitude H. Since given here is the length of lateral side, so the altitude is just the perpendicular distance between, or the parallel distance between the bases. So from this base to here, perpendicular from that base going downward. Okay, so this is the parallel distance between the bases. Okay, so if this is H here, we can form a right triangle again, and our hypotenuse is this lateral side, 40 meters. So given an angle of inclination of 60 degrees, we can use sine function. Okay, using sine function, we can determine h. Sine 60 is equals to the opposite h over the hypotenuse L. So record this h. Okay, we multiply both sides by L. We have L sine 60 degrees equals to h. Substitute 40 sine 60 equals to h. Therefore, h is 34.641 meters. That's your h here. Then, for the volume, you can now compute the volume using this formula. Area of the base times height. The area of the base is just the area of the circle. Area of the circular base given diameter, you can use pi d squared over 4 multiplied by h. So substitute 4 squared over 4 times h, 34.641. We have a volume of, computing that, we have 435.312 square, sorry, cubic meter. That's in cubic meter. Okay, next problem. A circular cylinder with a volume of 6.54 cubic meter is circumscribed about a right prism whose base is an equilateral triangle of side 1.25 meters. What is the altitude of the cylinder in meters? So let's draw that. Oh, so here's the figure for that. We have a circular cylinder circumscribed about a right prism. So we have a triangular prism inside a cylinder. Okay. So given the sides of the base of the equilateral triangle of the triangular prism, which is equivalent to 1.25 meters. So this, this is the base of the prism and the cylinder. Okay, given an equilateral triangle, so all sides are equal. What would be the altitude of the cylinder in meters? What is the altitude of the cylinder in meters? So given volume of the cylinder, okay, given volume of cylinder, okay, that's 6.54 cubic meters. Okay, so if we have the volume of the cylinder using the formula for the volume of the cylinder, we have the area of the base times the height. Okay, so the area of the base times the height. We have uh, we need also r, okay, for the area of the base, the radius of the circle. So given 6.54 equals to pi r squared times h. H is required. So let's determine h. Divide both sides by pi r squared. So this is cancelled. 6.54 over pi r squared equals to h. So what is r? We have to determine what is r. Uh, to determine r, let's proceed here on the circumscribing circle on an equilateral triangle or the base of the two solids. So if you have a circumscribing circle along a triangle, um, the distance from the center to the vertex are equal. Okay, they are equal, and that is the radius of the circumscribing circle. Okay, because the location of the center of a circumscribing circle on a triangle is called the circumcenter. Now, this is radius. This radius r, and r. So how to compute r? We focus on a triangle form, okay, a smaller triangle form. Say this one, okay, this triangle here with two sides which are r and 1.25. So how to compute that? Um, since this is an equilateral triangle, it means that the central angles or the angles formed by dividing it by the radius of by dividing the triangle by the radius by the line of formed by the radius of the circle, so they are also equal. They are also is, is an equilateral triangle. This angle here say theta, this is equal here. Therefore, uh, we can use 360 degrees divided by the number of sides, which is 3. Since 360 degrees over 3 is equivalent to what? That's 120 degrees. Okay, because the total of 360 degrees, divide that into 3 equal parts, we have 120 degrees. Okay, and since the other sides of this triangle, let's erase this, focusing on this smaller triangle here, we have two sides that are equal, which are the radius of circle. This is an equilateral triangle, which means that uh, if these sides are equal, the opposite angles are also equal. So if this is 120 degrees, when you add two equal angles, it should be 180 degrees. So in theta is equal to 180 degrees minus 120 degrees. That's 2 theta equals to 60 degrees. Divide both sides by 2. We have 30 degrees on each side. Okay. Okay, let me use beta para, so that we don't have confusion. This is beta, beta. So 30 degrees here, 30 degrees right here. So uh, we we now have interior angles. Okay, let's redraw the triangle here. This one. We have 120 degrees, 30 degrees, 30 degrees, and this side 1.25. So we can use sine function in computing the radius here. Or so using sine law, we take the ratio of the side with respect to the sine of that angle, of the opposite angle. So r divided by sine, the opposite angle of r, which is beta or 30 degrees, is equivalent to this side 1.25 over sine the opposite angle 120 degrees. Okay, so r is equals to 1.25 sine 30 degrees over sine 120 degrees. So r is equals to 0.722 meters. Going back to this formula here, we can now substitute r, which is 6.54 over pi r, or 0.722 squared. 722 squared equals to h. So h therefore is equals to 3.993 meters. That's the answer.